bottom eventually.
Okay, so at the moment we've basically been considering that's box. We've just been saying, okay, there's some force pulling box. Okay, but obviously on the other side of this, because we only like telling you one thing at a time, is actually man. This is Bob. Say hi, Bob.
Wait, isn't he the one that died in the book? He's been resurrected.
Okay, so even though this sounds strange, oh Bob,
It was your fault.
Just change his first name to Sponge.
Sponge.
SpongeBob.
This is the cousin of Bob.
Wait,
SpongeBob.
SpongeBob.
wait, guys, does that mean that SpongeBob's name is Sponge Robert?
Probably. Right, we've been calling this for some kind of attention force. Okay? So Sponge is applying some force on the box, a pulling force, but you know from pulling a heavy object what happens to your arm, it gets
Tired.
pretty tired. And that's because the box is actually pulling back on you. And this force, right, is what we are going to look at now, right? And it comes from who? Who wrote those stupid laws?
Isaac Newton.
Newton? Right, and which one of these laws is it?
The third one?
Okay, so his third law. Come on, we all know the third law.
Isn't it
For every action, there's an equal and opposite reaction. So if there's a tension force pulling on the box, that must mean that there must be a force to oppose that or resist it. Right?
Energy in equals energy out.
Yeah, so for every force there must be an equal and opposite force. So if we apply a force in one direction, there must be some opposite force acting in the opposite direction. And that force is the box actually pulling back at Bob. That's why if the box can pull harder than Bob can pull, the box is not going anywhere. And so if you try to pull something too heavy and you don't have enough tension, the box is not going to go anywhere.
Maybe that's how Bob died. He was
Possibly.
trying to pull the box
He
and
pulled
then
the
someone
box.
shot him.
You pull the box so hard.
Strain every muscle in his body.
And he died. That's how Bob died.
So, in a nutshell, that's Newton's third law, right? You guys obviously probably go into more detail, eh?
Yes.
We're not going to go into all the grimy details. That's all you need to know.
Sir, as long as you don't have to do electricity on time.
Yeah, as long as there's no electricity, we all Gucci.
Is electricity difficult?
Well, we all like. Kiana just laughs.
Okay, I got the highest mark first time round, right? And that was a 60.
60 something. Kiana got 60 something. That was the highest mark, okay?
I think the average mark, the second one was 40.
Yeah.
The average mark of the first one was like 30.
Yeah, it was bad.
It was a painful
And I gave one.
I'm going to have to edit off this video. Look at this. Right, so obviously particles can be connected in many ways. Okay, so there's some string, something elastic, right? Something solid.
A sword.
A sword, you
That
can
killed
connect
Paul.
something with a sword. Okay? So a rod is just something that can be modeled as something that is connecting two things. Okay? And usually when we model these rods, what do you think we model them as, Sarah?
Just the line.
Can you tell me about the mass of these things?
0.
Yeah.
Oh, mass of 0. Wow.
Because if we had to give it a mass, then we're going to change everything, right? So a rod is just something that's modeled as a rigid. In other words, it's not going to
Break.
not break. It can break.
But it's not gonna
It can't expand and contract. Okay, so it's rigid. Very important, right? Because we're going to be looking at strings. That's going to be funny. And they do change, right? So we're going to first look at rods, something that can be modeled as a rigid connector, right? With how much mass?
0. Otherwise, you've got to calculate that in as well.
No.
Oh, and 0 friction.
And yeah, for some reason they seem to be they're being kind to you because they took friction, or they gave it to you, or they told it's on a smooth surface. If it's a smooth surface, how much friction?
0.
0. Okay, remember that.
0.
Right, give me some examples of a rod. The most common one.
Sword. for
Something that connects a train.
a car, train.
Okay, so the tow bar on the car, we can model it as a rigid connector with no mass because where do we include the mass?
In the car.
In the mass of the car. Okay, we calculate the mass of the tow bar on the car. Okay, another one, Gianna said was a trailer, a train, and it's, what do you call those things? Carriages.
Carriages.
Something like that.
Let's say cart.
A train and its cabin.
And we can say sword as well. When we connect swords to human beings, other funny things happen.
Oh, you know what? They're fun things.
Then there becomes a cutting force.
You know the slicing force.
The resultant penetration.
Okay,
The
so
resultant spray of blood.
when we have systems like this, because if you think about all the forces we've done, we've only been looking at one object. Now that object's been moving in all kinds of weird direction and there's been friction and stuff, but there's not been another object connected to this thing, right? Now fortunately, we are only going to be looking at these forces in one dimension, meaning you're only going to have horizontal or vertical. You might have to resolve up a slope, but that's as far as we're going to get. Okay, we're not going to have objects connected in multiple dimensions, pulling in all kinds of weird ways. Okay, so one dimension meaning the force, the direction of motion will just be easy to work out.
Thank goodness.
So, do you guys remember Newton's second law? What the Newton's second law was all about this equation here?
Yeah, F equals MA.
Okay. Now, in a connected system, one of the most important things that you can remember is that we can apply Newton's second law to the entire system or to the individual components separately. The entire system or the separate individual components separately. And I think it's because of the individual components that people realize, hold on, there's a missing force in here. Because if you look at the individual components of something connected, the forces are going to be different to when you look at the thing in an entire system. Okay? And when we do an example, you'll obviously see. Okay? So I'm not going to, in your textbook, they have that lovely paragraph, and because I'm not in the mood, I'm not going to write that whole sentence out, but key point 5.1, that's kind of an important thing to remember, okay? It is basically the foundation of what we're about to do. If you don't remember that or don't understand that, you're going to have a problem. I see you want to ask a question.
Yeah. You'll see this. We have different textbooks.
Yeah?
What the hell?
Like, for example, her page 108.
What's 190?
Her page 108 is my page.
Am I missing the page?
No, I think it's just different editions. They've moved the...
Yeah, I know. Mine's also different, but don't worry.
Okay.
I'm the only one.
Wait, but like, it
Okay,
doesn't...
so you and Twitter
No,
have the
Dominique's
same.
like yours.
You and Twitter are the same one, and me and Zara. Wow, that's pretty cool.
That's a pretty decent look at it, so.
Okay, let's quickly have a look at the two types of system wall environments that you could have with the system, okay? The one that you guys have been accustomed to is the pulling force, okay? So that guy, Bob, is pulling on the box, and the box is pulling back on you, okay? What do we call this? When there's a pulling force in two directions. It's tension, okay? So which direction are the forces going? Yeah, towards each other. Okay, that does sound kind of contradictory, doesn't it? You think that the forces, remember where the forces are coming from. Okay, this is the force coming from the box, right? The force being applied in the box, and this is the force pulling on. Remember, these are the objects. And when we draw force diagrams, we don't connect the pulling force. We don't say Bob's pulling the box and put that force over here. Right? The force is being applied to this box. Right, what if this object is applying the force inwards?
Then it'll be thrust.
Okay, so that's going to be that way. And that way, we would have thrust. Give me a very simple example of thrust.
Aeroplane.
Not even an aeroplane. The most simple example where you might have thrust. In other words, pushing forces, two forces pushing into each other.
Aeroplane?
Driving a car,
Aeroplane.
you've got a trailer on the back. The car applies the brakes. What's the trailer going to do initially?
It's gonna pull away.
Push into the car as it's slowing down, right? And the car might have a braking force, so it will be slowing down, pushing back. So
Or when
you-
you valve right here and then the shock stop the car.
Exactly the same thing, okay? That is an example of thrust. You've got two forces opposing each other, pushing at each other. So now the force is pushing that way, and the other force is pushing, so we have thrust. And yes, an airplane is thrust, but it's a different type of thrust.
Airplane is just a bit.
Okay, now we get to this. Oh, gracious me, I hate.
So wait, when you give us our homework and you say like page, what version do you use?
No, I don't ever say page. I give you exercises.
Exercise.
I don't have a textbook. What page number?
Oh.
Oh yeah, you just have the E version.
Yeah, I just go exercise so and so.
I must say, it's confused me once when I was like doing mechanics as well. We were like, okay, page, I think it was like 104,
Yeah.
and then it was,
Okay.
we knew what we were supposed
I
to
didn't know that until now, so thank you for pointing it out. Now I'll just say the page with the funny red box that says key point 1.5.1. That page.
The weirdest thing, right, is that both of the questions have the same answer for
Like
A,
from
Yeah.
a completely different answer for B.
Yeah.
Is this exercise 5.3 that we're going to do now?
I think it's what page one come up, right?
Because I did check in my textbook, the answer is correct.
Yeah, 111 and 112.
Okay. Anyways, guys, let's have a look at forces and connected. So you guys know how to draw a force diagram by now, obviously. So what does it say? A car is towing a trailer along a horizontal straight road. So that's my straight road over there. You would use a ruler, obviously. The car has a mass of 1,500 kilograms. The trailer has a mass of 500 kilograms. So we will draw these beautiful cars like such. There's the car. There's the trailer. They are connected, but we're going to show them separately. So leave some space because you're going to have to draw some forces. What force is not always evident but always there?
Friction. Air resistance.
No.
Mass.
The weight of the car. What's the weight of the car?
15,000 newtons.
Yeah.
Okay. And the trailer is?
Oh yeah.
5,000.
Yeah, I always put G there. I know it's kind of naughty, but especially for y'all physics guys, maybe that's a good thing so that you not forget that you use a different,
So that you forget.
so you don't forget.
Well, I think it's just gonna make us forget to convert, because I will forget.
The problem is if you don't convert correctly here, you're already wrong. You need to use 10 for mathematics and 9.81 for physics. So be very careful. Okay? For physics, you don't want to have to write that number out here. It's easier to keep that variable in there until you need to put it in your calculator. That's why they have the number out like that.
Well, wasn't it on our physics paper that we wrote this year that it was 10?
Oh no, because I
You have to just read the...
Oh, okay.
Okay, forces that are obviously not always obvious are the fact that both of these have one force, A.
Contact.
Yeah, normal contact force. Both of them have one. They are connected together like that. So if we consider this as, remember, we can look at a connected object in an entire system, right? Because they are connected with something rigid, we can treat them as one system, right? And so we can actually combine the normal contact force and the weight. What would the combined weight be?
2,000 grams.
Gram.
Gram. Okay, they also gave us this car has what? Resistance to motion of 80 newtons, and the trailer has resistance to motion of 100 newtons. So in a combined system, what's the combined resistance? 100 newtons. How much driving force does this car have? That's 360, eh?
Yeah.
So that's what the question was. So when we are considering forces connected with a rod, the first thing we have to do is consider the entire system. And the reason we need to do that is because we need to find out acceleration. once we have the acceleration, we're going to use our acceleration to solve for all the accepted forces. That's why I haven't drawn them on here yet. I'm modeling this as something that's just connected together in one system. So let's find our acceleration. How do we find that again? Yeah? Force equals mass times acceleration. Remember, this is the net force. And which direction do you think we should make the direction of motion? Does it actually matter? No. But for the purpose of calculation, it doesn't. So why don't we just be nice and say, let's make that our direction of motion. Direction of motion. Should we make our acceleration in the same direction?
Yeah.
Probably, because it's just going to make life easier. Or make it more difficult. Or we can make it more difficult and make them different, but let's make it easier.
Let's not
Remember, these two things can be in different directions. Okay, but it's easier to just model them in the same direction. And you can normally look at your diagram and go, well, there's more force going that way, so the thing must be going in that direction. So forces in the direction of motion are what? Positive or negative?
Positive.
So we have 360 in that direction. And we have 100 in the opposite direction. Okay? How do we write in the opposite direction force?
Negative.
Negative. So minus 100. What's the mass of the entire system?
2,000 newtons.
2,000 kilograms, and A is what we're trying to solve. Somebody quickly punch in the calculator for me, or unless you're... Oh, I've got it right here. 0.13 meters per second. 0.13 meters per second squared. That's our acceleration in the system. Okay? I've just subtracted those and divided by 2,000.
Shouldn't you divide by 20,000?
Yeah.
No, not 20,000. Remember, this is the mass of the car, not the weight force. The weight force is mass times gravity, that's times g. The mass itself is without gravity. Okay, so quite a common mistake that happens. That's why, also maybe not a good idea to calculate. You can actually see the mass of the car. And remember, if they give you the force for weight, you need to divide by 10 to get the weight of the thing. Okay? Now we have the acceleration for the entire system. Okay? Now that I have the acceleration for the entire system, we need to consider the tension. So you see this rod here. And this rod we were naughty. We actually need to show the forces on here. So on your diagram, you're actually not going to connect it with a solid rod. You're going to show the two connections as two separate forces. There's the force that the car is pulling the trailer. So this box has got a pulling force on it. But what's it going to do back to the car? It's going to pull back. And what can you assume about these two forces? They're going to be equal. We'll call them equal and opposite. Now just get into the habit of labeling your tension forces. Because you know what's coming, right? 5 characters connected.
Oh.
So I will call this T1 because it's, even though there's only one connecting force here, I'm going to call it T1, so I'm getting in the habit of labeling my forces. Okay, we need to also split up the resistance to motion. What was the resistance to motion for the trailer? 20 newtons, and the car was?
80.
80 newtons. So now we're going to look at these two separate things by themselves. Was there any driving force for the trailer? No, obviously the car is providing all the driving force. So what we need to do now is we need to individually go and calculate their forces. Okay? So let's go and look at the first one. Direction of motion, still the same direction. We have 360. What you can also do, just so you don't lose track, is label what you're doing. Say this is the whole system. Then you know that this calculation was for the whole system. Now I'm about to work out, well, let's call this the car, or you could call this object number 1, whatever you want to do to distinguish it. Right? So I'm now doing for the first one. Right? That tells me that this is the one that I'm working with. So we can call this number 2. It just makes life easier. We're going to do the same thing. Okay? What's the forces? Well, we have 360 newtons going in the one direction. And what two forces do we have have the opposite direction. 80 newtons resistance, and whatever the tension is there, I don't know what it is. And that must equal the mass of the whole system or just the object I'm working with? Just the object I'm working. Remember, I'm not looking at the whole system anymore. Now I'm looking. Remember, these forces here can also be looked at separately. So the mass of this object is only 1,500 times acceleration. Do you think the acceleration is going to be different when we look at this thing in different components?
No.
Obviously they're traveling, they're connected. They have to be traveling at the same speed. So their acceleration is the same. So do you understand now why you need to work out the acceleration first? Because otherwise you've got two unknowns. Okay? Now before we go and solve this, we're actually going to go and look at the second one. Let's have a look at number 2. The nice thing is you're always, when you are working with forces like this, always going to have an extra equation. Usually you're trying to solve two variables and you have to go looking for two equations. Now you're always going to get an extra equation. Because we can also consider the trailer. Let's resolve the trailer. What's the only forces going in the direction of motion? Just the tension in the rod. What's the force going in the opposite direction? It's the minus 20 over there. It's the resistance to motion. What's the mass of the trailer? 500. And that's times acceleration. So guess what? You can pick which equation you use. Both of them should obviously give you the same answer. If they don't, you've made a mistake. So which equation would you think is going to be easier to work with?
The bottom one?
Yeah, the bottom one, yeah? So you take the acceleration, multiply it by 500, and we need to add 20, not subtract 20, and you should get blah blah blah.
Wait, why 500?
Because the mass of
this
this
trailer.
is only 500. So this is the whole thing now. This is the sequence that you would always do. You're looking at the whole system so that you can calculate the acceleration. Once you have the acceleration, you can calculate all the individual components separately. You should get, what was it, 85? 85 newtons. Now, very important, you're looking also at the value of this. This could be negative. If it's a negative number, what does that tell you?
Acceleration is the opposite.
It's not acceleration,
It's
the direction. The force is in opposite directions, which means it's not tension, it's
first.
thrust. Okay? What scenario do you think you're going to get thrust?
When somebody hits the brakes.
If you hit the brakes, remember, the car stops, but the trailer continues moving, so it actually continues going forwards, right? And so it's a thrust.
Well, unless it's like you get those solid ones. Don't you get those solid?
But you have a very, very fancy trailer that's wired in.
The trailers that are like basically connected by solid rods or something. So they stop it.
Even
I
if
think-
yeah, it is, but like
Yeah.
the solid rod, the trailer still has inertia, it's still forcing it backwards, and then it is putting.
Well, technically, if you hit the brakes just on the trailer, you could make almost tension.
You would increase the tension.
Yeah. So if you hit the brakes on both of them,
Then you would
make
Stop.
zero.
Okay, I want you guys to have a look at the next example, right?
or slow down.
Now I'm going to post my nicer notes, like these crummy notes in the textbook online, but we don't have time to go through all of these.
These plebby notes on the board.
But I want you to have a look at, I'm not going to use page number, I'm going to say work example 5.2.
We only get the whiteboard notes. When I go work example 5 on 5.2.
So have a look at 5.2. The first thing that they did was they looked at the whole system. Okay? Now this was a slightly different scenario. This is an example where something is on a braking force, meaning that the force from the first vehicle is in the opposite direction. But the same process happened again. Okay? You You look at the force of the entire system, and once you find your acceleration, you can look at the force of the individual components, right? And in fact, in this example, you've got a thrust of minus 30 newtons, okay? Now, the part of that question that I want to look at is the second part, okay? So this is where the vehicle and the trailer are moving down a slope. And what's the incline of that slope? 3 degrees, isn't it?
Yeah.
Here we have the vehicle. Here we have the trailer. Okay. They said the forces remain the same. So if you go back to the question, what braking force was there? 100 newtons. So this is my direction of motion. I'm going to set my direction of motion like that. Which way is the braking force going to be?
The other way.
Yeah, obviously the other way. There's the braking force there, and it's 100 newtons. That's the worst 100 newtons ever. There we go. Right, we also had friction or resistance to motion of 80 newtons. And on the trailer of 20 newtons. That's just friction or whatever resistance to air resistance or whatever. The combined resistance to motion there was just 80 newtons on the car, 20 newtons on the trailer. And there's two other forces here, well, many forces that we haven't actually put in. What force is always there?
Weight and the contact
Weight.
force.
What was the weight of the car?
1,500.
And the trailer. Okay, we've also got the normal contact force coming perpendicular to the surface. We're not going to worry about that. Fortunately, it doesn't make a difference here because it's perpendicular to motion. It resolves to nothing. One more force we've forgotten. What is this thing connected with?
Isn't it a tow bar?
A tow bar. So we need to put in our there's our connector, and we need to label it appropriately. We'll call it T1. Because in this example there's only one, but in the next example there's 5 or 4 of them.
Oh shoot. Oh my word.
And in one of your homework questions there's 10 of them.
No.
Yeah. Okay, so let's have a look. The first thing we need to do is look at this whole system. Okay? Let's look at the whole system. Tell me, Dominic, the forces acting in the direction of motion.
T1.
Okay, we have T1, and I'm going to put it there. That might sound silly, but I'm going to put it there. Now tell me all the forces that act in the opposite direction.
Isn't there still another force that acts in the direction of motion?
Yeah. In the direction of motion, no, only T1.
What about weight?
It breaks, doesn't
Oh
it?
yeah, it was on a hill. You're right. Sorry. Thank you, Kiana. I'm thinking of looking at, maybe I should scroll up here.
Oh, answer A.
I'm looking at answer A,
Yeah,
it was
me
on the
too.
horizontal. Okay. Yes, Kiana is correct. This is on a hill. That's the whole point that I skipped the easy one to do the more difficult one. We have the weight component here, right? Because remember, we are resolving parallel to the slope. So this force is not parallel to the slope. We have to split it into its two components. So we have the vertical and the horizontal, and the vertical and the horizontal. That's 3 degrees by the power of triangles, some good old geometry. So what side of the triangle is that?
Sine.
Yeah, it's opposite, so it's sine. Okay, so now Dominic, tell me the forces acting in the positive direction.
In the positive direction is
T1.
The
Okay, plus,
weight component.
so we have 1,500 sine, oh no, that's 1,050. 3 degrees, yeah, I forgot to multiply by 10. And we also have, is it 500?
I think so, yeah. 500.
5,000 sine 3 degrees. Okay, that's that guy over there. Okay, now tell me the forces acting in the opposite direction.
Is that 20 newtons?
So we've got minus 20 newtons,
Minus 100.
minus 100 newtons,
Minus, is that 80?
minus 80 newtons. One more to go.
And then minus T1.
Minus T1. Now, when you are resolving the whole system, do you actually need to put the tension forces in?
No.
No, because then you put an opposite, they're all going to cancel each other out. And so, only when you look at the whole system, you can ignore all these forces that you are trying to work out. Because our point here is not to work out the force, the tension forces or the thrust forces. We're actually trying to work out acceleration first. Once we have the acceleration, then we can use it to solve all the other little forces. Somebody with a calculator? Mass.
Minus 200.
So this is going to be 2000 A. And by the power invested in me in my calculator that worked its butt off yesterday, acceleration is 0.423. Meters per second. Okay? That thing you store your calculator immediately, and you put a nice little pencil mark there for whatever letter you used. Okay? The reason you want that stored is because if this is a combination question, you're going to need that acceleration figure every single time. So you don't want to have to go work out 1500 sine 3 plus 5000 sine 3 minus 20 minus 100 minus 80 divide by 2000 every time. So please store it in your calculator.
Terrific.
Okay, now that we've seen the whole system, let's look at
Spark joy.
just the car. Tell me the forces just acting on the car, Dominic. Ignoring this guy, so we have that guy. Sine 3. And any forces acting in the opposite direction. That's minus 100, minus 80, minus T1 equal to that.
Yes.
Now we could solve for T1 now, or we could just be a little bit clever and think, usually it gets easier as I work down the line. Okay, let's go trailer here. Why do they call it a trailer?
Because it follows it.
Okay. Okay, here we have 5000 sine 3 degrees. That's that force there, going in the direction of motion, and these, only that force align. Plus T1. Which equation do you use to work out the tension in the tow bar?
That one.
Well, it's a Christmas present. You can choose. Okay? Both of them, because they are there's only one variable in each equation.
I choose.
You choose any one you want, alright? Just make sure you plug the correct acceleration figure in there. Yes, Paul?
This one.
I believe you can look in your textbook for the answer. It ends up working out to be the same, right? It actually ends up being minus 50 newtons of thrust. Now that doesn't always work like that. 5 minutes to go. 5 minutes of torture. 5 minutes of torture. Right, I'm going to show you how to have a look in the textbook at the next problem. Now you can see where this can get very messy very quickly. And why labeling your forces becomes quite important. Okay, so we have, is it a train? And all its little choo-choos. Okay? How much does the big choo-choo weigh?
The big choo-choo weighs 8 newtons.
8 newtons.
Oh, it's a little choo-choo.
Okay? How much driving force does little choo-choo have?
3 newtons.
3 newtons. Okay. Now, does it have any resistance to motion?
Not quite, no, not quite, not 6 newtons.
Okay, there's resistance. Okay, now little choo-choo is connected to? How many little choo-choos?
Four tiny teeny choo-choos.
1, 2, 3, 4. Okay, these are connected together, but we're not going to show them as single connections, we're going to show them as forces. Okay? So So these two together, they will make T1. Those guys will be T2. Remember, they're the same force, which is actually in opposite direction. There's T3, T4. How much resistance to motion do all these little choo-choos have? 0.01 newtons, right? All of it.
Yeah.
And they all weigh the.
They're all way too
They?
They all weigh 2
Okay, how much do they weigh?
2 newtons.
2 newtons, and then we go and add some weight in it, didn't we?
Yeah.
We placed 0.1 kilogram of weight in it. So that basically, all of them are now going to be 3 newtons.
0.2 kilograms like anything.
Yeah.
We've got another seat. James.
Yeah.
Outside the window.
Oh, Mr. T, you want to look at our choo-choo. Okay,
Choo-choo trains.
how you deal with this problem is exactly the same. Even though it looks like horrible, you first have to find the acceleration, and so we have to look at the whole system. So don't get paranoid, just look at all the forces. Fortunately, this is not on a slope, so there's no hidden components here. So we have 3 newtons going in one direction, and all these tiny little, do we need to add and subtract T1, add and subtract T2? No, it's a waste of space, so don't write the tension. We're not interested in these forces until we find the acceleration. Minus 0.06, minus how many of those 0.01s do we have? And that must be equal to the combined weight. What's the combined weight of this choo-choo? 3, 6, 9, 12, 20. 20? Is it?
Yeah.
I mean,
12 plus 8 is 20.
yeah.
That's true. Is it 20 newtons?
Yes.
No.
Yes.
What's the weight?
Oh, it's
2
Mass. What's its mass? Not weight. Mass.
kilograms.
0.2 kilograms.
Wait, what?
You were correct.
You're
You
right.
Kilograms.
lost for weight.
2 kilograms.
Okay. What does that mean? Acceleration of 1.45 meters per second. Okay? So guess what, Claire? I know we're going to do this very quickly because we've got 2 minutes. I'm going to post your homework on Edmodo, so go look there, be there.
No.
I can write it on the board too.
Okay, no. Problem put on a motor.
How many equations am I going to have? If I've got 4 tension forces, what did I tell you? You're always going to get 1 extra. And you can use that last one as like a double check.
That's 5.
You should get 5 equations here. Okay? I'm going to look at all of these things separately now. Every single one. That guy, then this guy, then that guy, then that guy, and then that guy.
Why? We're not
Because we want to find all these little forces in between.
Well, if they're all like the same.
No, they won't.
The small choo-choos.
Because the weights are the same, they will always get gradually less. Okay? There's going to be more pulling force on the first one than on the last one.
Yeah, I think it was like
Yeah?
If there's 4 behind this one, right? Then the combined weight is 12, but it's being pulled at the same.
So let's look at the first guy. The first guy is 3 newtons minus 0.06 minus T1 equal to 0.8. There's my equation. So I can actually put A in already, and I can find T1. What is the answer? You put 1. So you would just take 0.8 multiplied by 1.45 minus 3 minus that.
1.75.
Okay, now we make the next equation. So let's just look at train number 2, just this guy here. So the only force acting in that direction is T1, and guess what? It's still in your calculator. So don't get here, because you're going to... The forces acting in the opposite direction, minus T2 equals, what's the weight of this thing? Remember, we're only looking at that individual component.
0.3.
And immediately plug into your calculator and find T2. And now we're just going to look at this guy here. Right, that guy there is T2 minus 0.01 minus T3 equal to 0.3a.
It's okay. Well,
And guess what? Then we have to look at this guy over here.
Which question is with 10 paragraphs? You said.
Question 7.
it would be funny if it was question 10.
Sure. You got 1.75, right?
It's alright, not me.
That was the. I also got 1.75, which is why I said there's an error symbol.
Oh, that was
Yeah, that might be the error.
That's
But I
yeah.
got 1.5.
No, I got 1.78.
Oh, then
What?
Maybe you didn't take the resistance to motion of the strain as 0.06. If you took this as 0.01, you might have got that. Who knows? Anyway, right. If they tell you something is in equilibrium, what can you tell me about the net force?
Equal to
0.
If something is in equilibrium, what's the acceleration?
0.
0, which means that the forces must resolve to 0. So I'm telling you that because a lot of your homework questions are going to be problems in equilibrium. Okay. Would you like your homework up on the board quickly?
No, let's. Well, how many questions are you gonna give us?
Not that many. In fact,
Only 12.
no, not 12. Only 7.
Only 25.
Only 7. 1, 3, 5, 6, 7, 8, and 10. And this is exercise 5A.
It's always the odd number. Okay, transform.
They are quite literally chosen at random.
Could you not choose 7 randomly, please?
I would like you to do 7 just once, and I swear,
Just once.
I promise from the bottom of my heart, I will never give you a question like that again.
Really?
You just have to do it once. You just have to suffer through it once.
Okay,
So
well,
what happens if you do? Then
Would you like? I actually did it now while we were.
we've got Mr. James on video, so we can hold him to that promise.
I'm going to delete the video.
No!
So there's my diagram,
Oh my word.
and there's all my little forces. Right? So have fun with that.
they look cute, but they're deadly.
They are they're actually very easy once you start solving them. The reason I want you to do question 7 is because you'll start noticing a pattern. Halfway through that list, you'll be like, wait a minute, I see what's going on. And it goes like that. Okay? And then it makes doing all of these problems a lot easier. So remember, we look at the whole system to find acceleration. And remember, sometimes there's no acceleration. And then we look at each individual component separately. Dominic looks like she wants to kill me.